Okay, maybe I start here. First of all, we have to thank Lei Yu that he also is willing to shift the presentation before the MIS presentation, so afterwards we can all have apéro together. So it's my pleasure to introduce you to Lei Yu. Again, he was here already 8 years ago, together in the same course, then nervous system. At this time, I think we had a workshop about computational, physical computing. Huh? And now I'm curious what the life brought to you in the last 8 years. So Lei Yu is a PhD from Tsinghua University, with a Master of Architecture from Harvard University. And he's like nervous system, he's a key figure in the computational design scene, but also in the digital fabrication scene. He's co-founder of Digital Architecture Design Association, which is important cooperation of Chinese architects who put a tremendous effort in digital architecture, design, and practice. Lei Yu's company is called Arachne Solution Workshop, ASW, which has recently drawn global attention by the intensive activities in digital design technology. And this will sound familiar to you, based on the philosophy of multidisciplinary in research and cross-boundary in practice. Arachne Solution Workshop has recently accomplished a series of projects by 3D printing and robot arm in architectural scale. Lei was invited to lecture at Tsinghua University, Tongji University, and now already for the second time ETH Zurich. Very interesting, and I'm very curious to see this also. Lei was selected as a figure of Beijing Design Week 2015 with this large-scale project Vulcan Pavilion, which is maybe one of the largest structures in 3D printed FDM or maybe additional material that I've seen so far. Now I just talked with him, and he will maybe present another project that is even 3 times bigger. So I'm very much looking forward to your lecture. Please welcome Lei Yu.
Thanks, Benjamin, for the invitation. It's my second time. It's very pleasure to be here again in the new building. I'm so a little bit jealous because it's so cool. Huh? 5 years ago, I came to ETH Hungerberg. Was in the CAD department. That's fundamentally changed my career path. So I'm very excited. I was very excited after I got back to China and did some practice. So a little bit pressure from nervous system because they had a very wonderful lecture yesterday. So I will try to find the big difference between us. One, probably you came in couple and I'm alone, right? Yeah, I think the difference between us, since Jessica dropped off from architecture major, I stay for almost 20 years in the architectural practice. So the scale probably the biggest difference between us. Since as architects, I'm always ambitious on make space, architectural space for human beings. So figure out a way how to use the machine. Okay, it's after the Industrial Revolution 100 years ago. There's the relationship between a machine and a human being. It's becoming more and more complicated. So in the former industrial period, people become a gear, part of the machine, and so that's the architecture job. They do the pipeline, they're doing the standardized work, so which is very boring. It become more and more boring. So there are also a lot of proposal and scenario and like how people dealing with a machine in the future. This is from Archigram, which is very famous. I think this one is Sigrid Brau-Cocan. She always use this picture because people want control machine instead of be part of it. So people want to step away from the gigantic installation and want to code everything and do the remote control with automation. Since we are experiencing great change, I would define it from analog phase to digital phase. It's a historical transition. You see the Fourier transformation. Everything is digitalized, like the sound wave and the music is a historical prototype. And it's like the data and the diagram is becoming a powerful tool for designer. So I want to say we are getting into the information age. We're going to get a new interface of design. It's not only about the drawing, in the city room, you do the boring work. You step away from the materials. Actually, we're becoming more and more, getting involved with our traditional, like 1,000 years ago as a craftsmanship. So designer is able to refresh its identity, a human being is is replaced by the robot, and the robot it's becoming like an automation system. It's very it's already it's regulated in car mobile industry, but why not in architecture? Because architecture is very heavy on human labor. So I got a lot of inspirations from Benjamin and Michael Hansmeier. It's the last time I visit. So it's totally opened my mind that there's a digital tool you can directly deal with the building material in quite different ways. Also, there's an inspiration from Archimedes. It's biomimicry research with megastructure use a robotic technique. Also, for the structure discussion, and it's like Philip Block last visit. We visit Philip Block studio. Is so impressed by their work. So they're dealing with a lot of design content together with engineering stuff. So it's a multidisciplinary research. We could do a lot of things from historical clues. Also, this fantastic work in 2 years ago. So the engineering side become a very critical points towards architects and all the other designers, because we have a lot of handy tools. You physically test the structure, which gonna be a very important component for your future projects probably. So ever since 2013, after I got back from ETH, I totally changed my work attitudes towards architecture practice. I started my digital things 5 years ago. So I happened to find this picture after I checked the data, it's like 2011. Yes, 2011. I made the first 3D printer as a pastime hobby. I didn't realize it's gonna change my life. Totally, I was excited to see everything goes together after I learned a lot of new technology like electricity, like MCU, computer programming, and mechanical design. It's only like making fun on my boring design work after my boring design work. So I think it's probably I could do some pedagogy stuff. So I went to Tsinghua for the PhD degree and had some classes. And this is the first one I connected 3D printing technique with some natural themes like a silky cocoon. So I moved the 3D printing extruder on top of the robot arms. It's like 4 or 5 years ago. I think this has same behavior between 3D printing, especially the FDM extrusion technology and the silk. They have the same physical features. Why not use them together for a structure? So I have my student test a lot of samples. We want to have a kind of a components with different kind of shape. After put them together, it could generate a shell, which has a lot of discussion on the building material and the forms. So I used Rhino watch 5 years ago. It's like maybe the first one in China. I do a lot of research and practice in school, and I didn't realize it's gonna be a real architectural practice. It's just like some pure research. This another one next year in 2014 in Shanghai Digital Future is a workshop of 3 weeks. So we step further with the discussion of the silk in different scales. It's like we want to have a mega structure scale, and we zoom it in and find the natural inspiration structurally from our research. This is the silk in the 250. It's very, very zoomed out. So we figure out that the section of the silk is very specialized in a certain form. So we want to have 3D printed in this kind of a mechanism. Also, they get a structure feature similar to the natural silk. It's kind of a biomimicry discussion. I also asked students to simulate this and test with a single load how it affects the structure in this kind of formation and configurations. Also, we use software to test how it works with a lot of different kind of forces. And finally, end up a mechanical design which could be a kind of an efficient way to extrude the filament. It's like a multi-threaded printing compound head which could produce, it's one-time produce the profile of the silk in a certain kind of a scale. So yeah, it's very quick turnaround. It's like only 1 week for mechanical design because we introduced 3D printer SLS technology. We get irregular parts overnight. It's kind of a Chinese speed. So it's finally it's just this is one time, the first time test, and everything works so well. So it's like already 2 weeks passed. We also introduced Arduino has the actual axis control, for the temperature, for the movements. So it's a compound project together with robot arms. This is the first test. It's very successful. We finished this project in 3 weeks, which is nobody trusts we're going to succeed. However, it's just worked out. So this is discussion. We have this kind of a configuration, and biomimicry prototype, and it's just like a spiral shape. It's automated, made by the robots, and it's continuous work. It's nonstop. You will find the clue from the video. This is actually my first experience with KUKA robots 4 years ago, and just play with it. It's nothing about the business. It's just kind of having fun in the summer, and it's not serious attitude, whatever. But the next year after, it's like I'm thinking like so my design attitude changes because I did a lot of mechanical design. Everything I want to have a chamfer, fillet, corner, whatever. It's just kind of control myself because I haven't. That's too bad. I'm so depressed because I'm going to the engineering side instead of like poetic architects. So we go back to the engineering side, and it's why not use this technology with the traditional material like concrete? We use 3D plastic filament together with concrete. It's kind of a mixture. It's kind of save my heart from the embarrassment. So we keep using Rhino walls. It's a fantastic plugin by Professor Philip Block and Ripperman. It's because we have only one single material. It's plastic. So we want to have the big coverage structurally. So we have a form that we planarize. We tessellate into pieces, which could be printable by our custom-made 3D printer. There's a lot of geometric discussion because it's it's like the planarization. It's very difficult thing. So we use a Kangaroo. It's a plugin in Grasshopper a lot and figure out our own way. So the reason why we use the load, the test, because people are going to go underneath it. We have to guarantee it's safe enough. So after we put 20 kilo above a thin shell, only 2 millimeter in the thickness parts, is very surprised that it's actually can have more discussion in the texture tile. So we developed a zip code, the generation code on our own, because we want to reduce the material cost and also want to have a silky skin back from our former research. Also, the concrete is the first time very dirty work. However, we are happy with it because architects never, in school, you never play with real material, especially for the concrete. It's a lot of chemical reaction, also very nasty job. So we are pretty happy. We have a concrete extruder together with a KUKA Agilus robot. We wanted this kind of semi-automatic activities, so all the pieces is digitally parametrically controlled. So this is the process. And it's a test. We are actually pretty succeed. It has a lot of concrete. It's like a silky concrete or the fiber concrete reinforced. It's a typical concrete research. And after this project, I got a call from Symposium, the biggest concrete. Oh, you figure out how to make silky concrete. This is a confusion. No, I mean, it's just a mixture. So the scale actually we were very bold to scale it up and to cover a lot of people. It's like a 5 meter, from corner to corner and 3 meter tall, and people literally stay underneath it safely because we trust is that the concrete will to frame every block to give rigidity enough. It's the light. There's a video. Actually, after the Shanghai Digital Future projects, still concrete, and I went back to Beijing and met the curator of Beijing Design Week, and she's very interested in our projects. Why don't you make a bigger one, right? It's a public space, so it's such a challenge. We have to finish this project before the opening ceremony. Like there were only 2 months left. However, we want a challenge. This is the final shot. It's like we named it Volcan Pavilion because we want to use the rhino walls use gravity as the internal force to make the form. So it's like the volcano eruption. This one is fairly big because it's a mixed-use, very high-end commercial space. So we have 500 square meter, had to be dominated by the installation. So it's actually we just step further with like a 12-meter diameter. 12 meter in diameter is a circle with 3 identical compartments. Each one is identical, but with totally they were on like 2,000 pieces together. It's so difficult to figure out in such a bigger size because firstly we have no experience for such a big installation, and we have to finish that in 2 months, and everything is just from sketch, from zero situation. We actually finished the design quickly because the experience borrowed from the Shanghai projects, and we launched 3D printing quickly. So it's a temporary installation, so we have to figure out a way how to put these together with a certain kind of precision, and also we have to control the tolerance. So it's such a big one. If any single one misses the precision, the whole thing probably gonna fail. So that's my workshop, in a very traditional courtyard house. The whole space is covered by all kinds of pieces, the 3D printed pieces. We actually had our own patent 3D printer. It's developed from my stupid little one, So now I'm able to print 1 cubic meter in size. So we regular size is 50 centimeter in cubic. So we just scale down every piece within this scope. And there's a lot of installation work as a volunteer from my students. We have a lot of trouble to do things assembly on site because there's no scaffolding. This piece is kind of a relay. It's one by the other. If one single thing has arrowed, all the other has to be taken off and replayed again. So we use the technique from one side, both sides at the meet in the center, and also the zip tie become a critical connection to help. And there's a lot of pressure from the schedule. So we are for the first week almost lost our confidence because nothing happened for the first week, and then another 2 weeks we have finished such a big installation. So I was thinking to escape Beijing if I didn't get it worked out. So finally it's pretty good. And you find a scale is from the references. There's man in the middle. It's most critical points of the 3 identical big components meet together. It's like we have a lot of unskillful students, but it came out pretty successful. It's this silky feeling. You stand right underneath the canopy, and it's just a wonderful moment. And it's some few shots. And it's during the Beijing Design Week, which is about 2 weeks, we welcomed a lot of visitors because they were so interested in 3D printing, and we call it 3D architecture. And also there's a Guinness World Record from the client side, and they said we want to promote their commercial space. So there's interesting, I want to mention this because the Guinness governor came and holy, how do you want to apply this Guinness World Record? I think it's fully 3D printed. No, it's the nail over there is you buy it in the hardware store, right? So I think it's 3D printable. So we spend like $600 for 3 nails to prove that this could be 3D printable. So it's which is like 10 cents US dollar only, but it's like 2,000 times more. This is the dismantling is a very sad moment, but it's the way to test our calculation based on the Renovault plugin. You know, it's just prohibitable collapse. And it was garbage finally. So we keep going for another commercial project. After we're very experienced with making a bigger space for human being. You know, there's clients that want to have an exhibition in Hong Kong, but they have a specific requirement for the exhibitions. So another requirement is that everything has to be installed during overnight. So this one, as I mentioned to Benjamin, it's 3 times bigger than Beijing Design Week's one. It's over almost 300 pieces together, and it's not symmetrical. It's everything. It's very free from the irregular shape. So we figured out a way to accelerate the installation just by screws. You know, so every single piece is screwed together, and like this. That's exactly the speed Hong Kongese, the craftsmen, the professional they make. They finish the whole thing like within 8 hours. There are 20 staff working around. This is like they are so well organized. Everybody knows what they're going on. Also, they don't need a director to say, hey, you do this, you do that. This is automatic robots, somehow like that. So this opening exhibition and this construction, that's everybody know their own position. It's amazing. And this is the final auction after the exhibition. So you will see how big it is. But we didn't apply the Guinness World Record, which is we see the stupid thing. As you say, it's nothing about design, right? So that place has happened. That is in Hong Kong. So the clients that want to reuse it, this is another installation in Beijing. They just ship everything back, screw it out, and screw it in again. It's very quick. So this the Silky scheme. This video will represent the Silky scheme we have done like for the past 3 years. So we keep our research of making things bigger and crazy, more crazy, because it's kind of ambitiousness. Like as an architect, you want things to scale it up, scale it bigger and bigger. Like in China, everything goes crazy. We have a very high-speed construction. We have a huge building industry. You know, it's becoming say like test field for all global architects. So we go back to the traditional material because we have been working with plastic for like 3 years and realize it's not an ideal one for the architecture because it's cracking easily. So get back to the traditional material, especially like wood and concrete. And we had 3 years continuous Tsinghua workshop. So we had 3 workshops with robotic timber structure. Each workshop only 9 days, so everything goes like just over and over without any stop. And so we pretty succeed for every workshop. This is the first one in 2015. We want to use to create automation system to use timber structure, very simple rules like bird nest. So we have a lot of inspiration from this. This is the second time I use a robot. It's just you know, it's when I was like younger, you know, it's like 3 years ago. I wanna try a lot of different things. This one we use one single robot, but it's a gripper, but there are a lot of tools around. So it's grip one single wood steak from McDonald's, like chopstick box, and you can make the workflow continuously. Also, like cut in a certain length and make the notch with a certain angle. So each one is has a very special relationship with the neighborhood. We heavily rely on the computation result. So it's the workflow, whatever. So there's a video that gave the whole story. So we have like 400 wood studs, and in different lengths and with different angles. This is one single robot work overnight, 6 hours to make a bird nest quickly and efficiently. There's only one thing involved with human labor is like to glue them together because it's only 9 days work camp. So we probably have another version with fully automatic system. So for the next year, I'm going to go quickly. The next year, we keep making things bigger, and it is we became more serious than the first year. We want to use a reciprocal structure. We have some historical hints, and I want to like keep the wall system because it's using one single material for a bigger space. It's very smart solution. Like for us, we have one single like timber structure, but we use the strategy of interlock to make the space. This is the test. And each wood struts has like different notch. Let them fit together. Here. It's also robot team. This is the final. It's a 9 days workshop too. It's cover one little girl underneath. For the third year, so we want a lot of people get inside in the structure. So we made on top of the structure, we use the branch structure technology and other program called Solid Thinking from Altair. Is inspiring. We discussed some natural phenomenon about how to make a structure lighter and stronger with less material. So that's how it goes. So we split the whole structure into two kinds of typical components. One is joints, the other is a connector. We use wood, the timber wood, round one, and for the connector because it's kind of one single strategy to solve all the kinds of angles. And also their water tube to connect them with a lot of variation and adjustment on the relationship. And this is big robots. We had some tests of how to make the work path to figure out the connector with a certain kind of within a certain kind of a range, because the robot always, it's not very friendly due to its mechanical constraint, especially the singularities. So we developed a lot of, we have some tests on how to put things in one position and have all the angle work out with this very simple cut milling strategies. So there are totally like more than 400 joints and 800 wood struts, like produced by one single big robot for 3 days only. And that's the finished one. That is like 10-meter long bridge, and I'm the weight load to test the rigidity, and it works pretty well. So that's the research. The next phase, I'm going to talk some commercial projects based on the robot and 3D printing. Since we have a lot of big 3D printers, and we also have the technique how to make things like together. And like for this instance, it's a curtain wall system. It's a corner structure for a 3-floor tall building, and this project, we use almost like 10 tons of PLA because the client is very crazy. That made us very crazy too. So we want to challenge the size again. It's like 2,000 kilometer away from my office, so everything has packed. We have a big truck carry everything over there. So that's the view. As we also do the one-to-one prototype and to prove our client, persuade them this worked out. Also, the lighting system are also embedded. It's like one single solution for everything. It's a construction site, and you can tell the scale from. It's a 3-floor building, and it's pretty apparent. It's got attraction from the corners, the street corner. So we also developed the curtain wall connection system. It's like there's a lot of tolerance. There's errors during the installation because the worker, they never had this kind of experience. So I will tell them how to make it, but they're really slow. So we have to find out a way to counterbalance the tolerance. So it's a lot of connector design and also different angles to make the kind of compound structure to stabilize the whole thing. It's the lighting at night. There's another one nearby. This is the toughest project we have done. It's not commercially, technically, and management. It's a lot of bad story, but it ends up pretty successful because it's built. Yeah, we're gonna. The client asked us if it's very silly cube box. How do you can make it up? Has a like gift wrap. So we think about it's a net wrap around. We have just there's internal force like shape the web like from the balcony or from the entrance. They have different density and because of the represented by different forces. So this. The developing algorithm is very simple. It's the box. So I have 3 kinds of threads interwoven together. And the web is deformed. Firstly, it has a thickness, and then deformed by the balcony. Extruded out with a lot of strength. And the threads is making the shape like interwoven together. It's the most crazy moment. And the form. This is how we split parts into 2 kind of a typical thing. And we also do the one-on-one scale prototype for the proving. And this is my 3D printing farm. And we also have a lot of trouble during the installation. We have to, because each member is different from all the others, with totally 3,000 also. So we have number, we have label everything. We also want to label the relationship with the neighbor, so each single piece has a lot of codes to guarantee its position is right. So we have a installation manual as thick as this, like an encyclopedia. And it's the final. This the curtain wall system we developed, and how it connects with plastic. So everything we have to deal with the on-site situation, because it's like 2,000 kilometers away from my office. So everything has to be carefully tested before the logistics. And it's the lighting. So the light is on the back. It's strategically embedded during the installation, so you'll never see the direct shining. That's kind of a pollution to eye vision. So there's drone shots. It took us like almost 2 years to finish these projects, like half a year design and the prints, and almost 1 year to wait installation, because the client doesn't really appreciate our work since it's too expensive. So it almost bankrupted, but finally it got built. We have so a lot of bloody footprint during my digital practice, because there's no example to show how it works. If it's, it's the client always worry about, if I spend a lot of money, it's a big risk, gonna take a lot of adventure, so it's not safe. So we go back to the research. This 3D robotic spatial 3D printing, we call it the 3D printing framework, meshwork. So we discussed the different typology of 3D printing, because most like a contouring craftsmanship is layer by layer based. But we want to see things goes up quickly instead of just waiting over there. So we use robot, because the robot has like 6 axes. It's spatially capable to make things different from layer by layer style. So we developed algorithm with it's a collaboration with Chinese Science Technology University Mathematics School. We have a lot of very deep coding in C++. So we figure out how to manipulate the robot has scientifically, because you're gonna have a lot of trouble, the collision trouble, also the extrusion trouble, material trouble. It's just a lot of things we have to overcome during this 1 year's research. So also the geological logic, how we group them, and we just calculate, we reduce the calculation amount. We have to group them scientifically, and just figure out the working paths one by one. So it's kind of the process. It's pretty flexible. It's a continuous, non-stop, no human involved generation 3D spatial about 3D spatial printing. So there's like
design, sculpture, and surface modeling. It is extraordinarily unnatural to fabricate frame shapes using FDM 3D printers, because they are fabricated layer by layer, resulting in a slow fabrication process and low quality products. In recent years, various fabrication systems have demonstrated that the use of a robotic arm equipped with a custom extrusion tool can more efficiently fabricate frame shapes. In this work, we propose a fabrication sequence design algorithm to search fabrication sequences for general frame shape fabrication. The general fabrication sequence is collision-free and guarantees that the printed structures have small deformations during the whole fabrication process. In our experimental setup, we allow the extrusion head to have different orientations for fabricating different frame struts. During the whole fabrication process, the printed parts should be in a static equilibrium, and the extruder should avoid colliding with the previously printed parts when it moves.
The air part is toughest.
The fabrication sequence searching problem is quite challenging, as it is essentially a dynamically constrained searching problem. The collision detection between the printed parts and the fabrication candidate struts is sequence dependent, as is the printed node deformation. To solve this challenging problem, we develop a divide and conquer strategy that first decomposes the input frame shape into several layers via a constrained L1 optimization method. Then, we find a feasible fabrication sequence for the individual layers via a local optimization method, together with a backtracking strategy. To verify the validity of our algorithm, we build up an experimental robot system. Finally, we compare our method with the FDM technology by simultaneously fabricating a bunny head frame shape of the same size. It can be observed that the fabrication time and quality of our method exceed that of the FDM technology.
Okay, actually, we have been taking a lot of reference from ETH, especially Professor Matthias' work, because it's exploration across the boundary, like to all kinds of possibility towards robotic fabrication for in the architectural language. So especially for the traditional material like concrete, we went back to the concrete because we think we had a lot of project that's plastic. You know, it's just expensive and it's like it's the endurance, the climate not friendly, you know, so we have a lot of trouble with the clients. So in order to keep the business going together with my research, so we think it's probably there's another way, you know, to transform the traditional technique like slip form. So we find this reference also from this important, it's kind of a milestone for dynamic cast towards slip form in Matthias' research. So what we figure out it's possible. Firstly, we copy this idea, you know, take a big reference because it's gonna be another discussion instead of a structure. It's a structure element which is very sensitive towards the building industry for the safety issue. So we think if we are able to make this as kind of a declaration for the energy eco-friendly building facade, so we translate this idea to another discussion, which is for more productivity, because it's for the concrete is very, very difficult to deal with. It's a chemical reaction, so it's a long-term research. It's slow and it's hard to control the shape. It's kind of a low chemical transition, whatever. So we have to figure out how to make things quicker and bigger. That's the it's a project we have done recently. It's the process So we're thinking for robot, as we always used in our research, there's only one robot, but it has multiple functions. It's kind of a simulation to human arms. It's like we have one or two hands. We do different things with two hands, with different tools. So if a robot can have like a kind of multi-function hands, like in this case, it's gripper, and we are able to increase the productivity like by time saving. So we developed this gripper which is very strong. We have the mold there, it's a square mold because it's cheap. It could be found easily on market. But we have multiple molds, so the concrete sits in the mold for a certain amount of time. It's become kind of greasy. It's like a certain kind of situation that's able to form easily, but it's not collapsing in that situation. So we are able to increase the efficiency. Also, there's a steel core in the center. We use the radiator. It's a typical radiator as a center. It can give a lot of support for the concrete. Also, there's a thin wire web to prohibit it from collapsing, especially increase the rigidity as a real building component. So this is the projects we have done in our campus with 115 columns. We finished this in 1 month. From the it's like every 10 columns every day, and we use half months to test the system and another half months to produce. And it's also interactivity because we have a sensor. There's a light between 2 columns at the bottom. And during the night, people approach. It's kind of an interactive reaction with the human being. So it become a kind of, it's not a wall, it's a separation line between the pedestrian and the parking lot, but it increase, it's another like description, it's kind of a thing represented modern technology. It's a kind of a promotion for the campus. It's also used robot. So we also find clients. So they have a huge projects. It's like 500,000 square meter. They want something new with robot. So we persuade them like if we have this kind of a configuration on facade by robots, it's like one solution give a lot of variations upon the analysis, the solar energy distribution analysis. So you get like kind of a good looking. At the same time, you have like better interior environment. So let's go back here. So everything is you can parametrically control in computer and get the data back to a robot, and you have one single modes that give different kind of profile. It's a kind of a sculpting the facade in very simple method. Also, you have the round corner. It's like twisting shape. It's continually flowing on the surface. So it's just whatever you want. We just change the parameter. You get a different lookings. So we're getting halfway, we have to coordinate with Norman Foster, and they kind of interested. So we're on the way to make things a lot bigger as a skyscraper. Yeah, the facade part of it. Yeah. All right, that's the latest one in my office. So we're doing research, we're doing practice. So we writing on both lines. We have to survive. We also want to be the advanced architect in the same time. So it's like my business and my research in a good shape. Thank you. So same, anybody has question? So if no, we're gonna switch to the final review. Yep.
Thank you. Amazing work. I have a question about the facades you showed. First, like the first one, let's say, the one that was at the corner, how long did it take to produce? How heavy is one component? How thick it is?
Yeah.
And one more last question.
Okay.
Does the plastic react toward the sun? It's a very like heat-sensitive material. Did you have any feedback on that?
You can repeat the last question?
The plastic, it's plastic, right?
Yes.
Yeah.
Yeah,
So
I
does it have any reaction toward the heat as you installed it afterward? Or
I understand that. That's two projects, right? The first one, we're working on a section size of 200 by 400 millimeters. And we also put some bubble things inside to reduce the weight. So from the material calculation, currently it has the same weight with the typical curtain wall, which is 100 kilo per square meter. So we can still reduce the weight by adding more substance. We like doing that research right now. So we use very regular material on market, so not like the one on the first floor is a very special one. So we want to use the material we can get from market easily to keep the price low. So that's a different discussion with the second question is solar radiance upon the plastic. That's a very serious problem. So we have multiple coating on the plastic prints. The first layer is the gel. It's because PLA is very smooth. It doesn't. If it's exposed to the air, it will gonna, have a lot of crack. So the first layer is gel, and the second layer with some mud, and the top layer with the paint. So in that way, that surface has stayed there for more than 2 years. And except the pollution and the dirt on top of it, it's still fine. So we say probably it has 5 years possible for another 3 years to go. And the clients it's okay. I think this is like special thing, and they want to promote their products through the latest technology. So they already have the money pay back. That is a lot of labor work. So it's architecture practice in the human scale. It's really muscle work. Even though you have a machine, you have robot to help you, but you still have to serve robot by your muscle, right? It's like carrying the concrete, carrying everything. So to feed the robot with a lot of forces. Yeah, that's it.
So both projects have a surface treated, right, afterward?
Yes, yeah. For the concrete project, we have the white paint. The color of the concrete is hard to control. It's a different moisturizing condition. We'll have different colors. Also, there's probably has some top surface grinding is in case when it's slipper form, it has some arrows. It's a very tough surface. You still have to sand it.
Yeah, thank you, Lei. Also, seeing yesterday the fantastic lecture of nervous system, now yours. Definitely, there's the difference in scale. You address architectural scale, and you always have to deal with bringing discrete elements together and the tolerances. But you mentioned also, and this I heard yesterday as well, 3D printing, the problem is the material. Huh?
Yes.
That's related to Mania's question also. So then you show a project made from wood and so. Yesterday we saw also then maybe stepping back and maybe just printing the mold or so. Where do you see the future there?
It's hard to say the future. Yes, we have a 3D printing concrete, which my professor Xu Guo is doing, but it has a very rough surface. Still have human labor involved to treat the surface, right? So I think slipper form is we have a lot of possibility with slipper form for the panels production, right? Especially like a balcony and the column, the decoration, also the like some decoration. But for the structural components, it's very, very sensitive regarding to the building code. So I think robot is replacing human labors. Everything probably will be precast in the factory, and its data flow is the backdriver to control everything. So architects are able to stay in the cozy chair again and monitorize everything going on in the factory. But first, we have to set up the typical thing. We have to set up the example to prove it works. It's better, has better quality and better budget, and also the eco-friendly discussion. Yeah, the paradigm should be changed quickly. If we actually in China we have a lot of trouble with the construction worker and the labor. Most of them are retired. The new generation won't take a place because it's not a decent job. So it's a lot of pressure from the industry. So as an architect, I think we have the responsibility to solve the problem, not from the design side, also from the production side. Yep.
Maybe also a question, because I noticed that often in your context, like how do you combine research and the commercial products? How big is your office, for example? How many people are working there?
Oh, I have 5 permanent, including me. All of them are designers. They are multi-capacity, has different skills, but everyone know the whole process, how to work with machines. And we have a 50 big size 3D printer. As long as there's a commission, we'll build more based on the design. We have FDM experience for over 8 years, so we are able to make bigger one. We have 3 KUKA robots, and we're getting more because it's not enough. We want to put the robots the same as the one downstairs, but we are independent company, not affiliated to any institution. So we have to make money from our projects and pay money back to the robotic manufacturer. But actually, the Shanghai KUKA helps us a lot to save money, because these kind of people is very, kind of cool to make things.
You have 10 FDM printer per employee.
As long as the one you want to have, we can produce more employees.
Maybe as a side note, so if you want to get nervous system for a lecture, you have to offer a botanical garden. If you want to get Yuli here, you need to offer a nice ski resort.
Yeah. Yeah, that's the bonus for this trip.
Oh, thank you. Any more questions?
All right. So they can't wait for the final review, I think. Okay, thank you, everybody.
Thank you.